Okay, I've filled in some details here. Again, hopefully you did this yourself. If I've done this correctly, and double check me to make sure I have, the derivative of your y of t function is 4 over pi from the chain rule, because that's the derivative of the inner function, times the reciprocal of the inner function, since you're taking the derivative of a natural log. So we get this, and this simplifies to this. Put this denominator over common denominator pi, and then express it as a simple fraction. You'll have a pi in the numerator, pi in the denominator. They'll divide out, and I believe you end up with this. So that y prime of pi over 4, well, we just substitute pi over 4 for t, and we get denominator pi plus 4 times pi over 4, which is just going to be 2 pi. It'll be 4 divided by 2 pi. Now, if 2 pi was 6, we'd have 4 over 6, which is 0.66, repeating about 0.7. Now, pi is actually about 6.28, and intuitively that's going to bring this result down to somewhere between 0.64 and 0.65. So I kind of randomly picked 0.65, didn't think too hard about it. But I actually think, well, let's see, it's more like 0.3. It's probably going to be more like 0.64, but I'll stick with 0.65. Okay, now our delta y then is going to be what? Well, the difference, according to our tangent line approximation, not the difference that we get by actually plugging numbers into the natural log function, is going to be slope, which is 0.65, because that's our derivative, multiplied by this distance here, the 0.02. That's going to give us 0.013. Not much different than the magnitude of the change in x. Okay? Well, we calculate our delta y then, and what was our calculation? It constituted y prime of t times delta t. Okay. And, you know, you see the numbers down here. And that's going to, this one came out approximately negative 0.014. And this one came out approximately plus 0.013. Okay, so what does this do to our value of f of xy? Well, if x changes by negative 0.014 and y changes by 0.013, we can calculate our change in x squared y, because actually I can't say what I was going to say, so I'm going to have to develop it. Okay, let's think about it. If we just look in the xy plane, and I started off badly because I don't have good vertical there, but we'll have to live with this. Our x and y values are what? 0.69 and, I'm sorry, square root of 2 over 2, which is approximately 0.707. So we're somewhere in the neighborhood of 0.7, 0.69. So we'll just say, okay, this is 0.707, 0.69. Being inconsistent with the number of significant figures, should have written that down 7.1 just to kind of be consistent. But there's our point. Okay, now here's x, here's y. We're going to move in the x direction. How far are we going to move? We're going to move actually in the opposite direction. Let's fix that. We're going to move negative 0.014. So if this is our point, we're going to move in the x direction negative 0.014. We're going to move in the y direction positive 0.013. Three didn't come out very well, but hopefully you get the idea. Okay, what's the effect of moving this far in the x direction and this far in the y direction? Well, this depends. This negative 0.014 movement is done with constant y. this 0.013 move here is done with constant x. What does this suggest? Well, hopefully, because we've talked about it, this suggests the idea of a partial derivative. The partial derivative of this function with respect to x tells us the rate at which the value of the function changes when for a change in x. Okay, so that ratio of the change in z per unit of change in x. And similarly, the partial derivative with respect to y is the rate of change of this function with respect to y when x is held steady, when x is held constant. And that would correspond to what goes on with this change in y. Okay? And there's a little more, I'll just mention it, you might not be able to grasp it at first. But this is small. This is a small change, this is a small change. We don't expect the partial derivatives to change much between here and here, do we? So whatever change we got down here in z, whatever z change corresponds to this negative 0.014 displacement of x, will probably be about the same as the change we get if we move from here to here. So if we add what we get when we move from here to here to the change, if we add the change in z due to this movement plus the change in z due to this movement, we probably get the change in z due to this movement certainly plus a change in z due to this movement. We get something very close to that, so we get a pretty good idea of the change in z if we move from this point to this point. And of course, why would we move from this point to this point? Because if we change t by 0.02, this is how far we have to move in the x direction, and this is how far we have to move in the y direction, so that's where we're going to end up. Well, we're going to draw a picture. I'm going to draw a three-dimensional picture, a pretty familiar three-dimensional picture, and see how this pulls together.